Okay, so before talking about the log Kummer correspondence, I need to talk about the Kummer maps in a single log link. So Kummer maps. And a single log link. So I guess I should call these Machizuki Kummer maps. Because they're not really, I don't know, they're nothing I would recognize as a Kummer theory. Well, a little bit, but so let me just start. So what we're going to do is we're going to have so we're interested in this log Kummer correspondence. So let me write what that is. So we have this log Kummer correspondence. Okay, and we have this core here. Okay, and these are a bunch of log linked. So here, so log pre up here, log pre. Okay, so these are a bunch of log linked copies of a field, of a p-adic field. So K is a finite extension of QP. This is the algebraic closure. These things here are field isomorphisms called the Kummer maps, or we'll call them Machizuki Kummer maps. And that's a C here. So this is this core here. And so all of these fields are log linked. By definition, we'll have something like Ki bar is Ki minus 1 log. So as a set, it looks like Ki minus 1 bar cross, and then we perfect it, and then as we recall, this has the field structure pulled back from this isomorphism of fields from log post. Okay, so there's a bunch of field isomorphisms going backwards like this, and so what I want to do is I want to examine what happens on this base field when, say, we go around a loop like this, so we go backwards. And so the claim is that when you do this on this base, this core field, then all you get is a logarithm. So this will just be the partially defined map, which is a logarithm here. So the claim is that this loop is equal to the logarithm on the core. Okay? And so to explain this, let's restrict our attention to a single loop here. So here is what we're going to have. So let's look at a single loop. And so this is log pre. This thing here was log post. And then we had these two Kummer maps, the Machizuki Kummer maps. Okay, C. Then we had this one, Kum 1. Okay, and so okay, so the goal again is I'll just restate this again, is that this composition zero inverse, this is the logarithm here on the base field here. Okay, maybe I'll omit the bars in this thing. All right. So to do this, we need to describe what these things are. And so according to Machizuki actually describes these in terms of Frobinioids, and these fields will actually be interpreted inside a pair consisting of a topological group acting on a monoid. Okay, and so so by, let me just say, Okay, so let me just say a little bit more about what these things are. And in order to do that, I need to discuss some of the Anabelian geometry. So to make this make sense, I have to talk about what these maps are explicitly. And then I have to disentangle some things. Okay, so so the Anabelian procedure is as follows. So so let's start with a single. So we're going to start with this is what's called the Etale version. Okay, so we start with pi in here. So it's going to be in pi 1 zc bar. So so this is going to be so z is going to be a curve of strictly value type. So meaning isogynous to P1 minus 3 points. And isogeny is an Etale to Etale correspondence. And so this makes it so that it has a field of definition, a number field. But we're gonna take it defined to be over a p-adic field. So K is a p-adic field, so a finite extension of QP. So using Corollary 1.10 of Absolute Anabelian Geometry 3, which uses a bunch of other papers. So in particular, the Absolute Anabelian cuspidalization of proper hyperbolic curves, the Absolute Anabelian geometry of hyperbolic curves, Galois sections of hyperbolic curves, and I'm not sure what else, but those papers are certainly used. And so you have to kind of like backtrace them. But what ends up happening is that we end up getting a field. Okay, so this is my notation for the interpreted field from the fundamental group. And it's going to be contained in a certain limit over S. So these are going to be subsets. So first of all, the fact that you can do subsets means that you can recover the closed points, as you can see here. I can remove them, and then I can do the cuspidal abelianization. Okay, so there's a bunch of things going on in this definition. Okay, so S, so the CAB is this cuspidal abelianization construction. So it's a subquotient. So what we'll do is we're going to take this. We'll be able to recover the closed points of the number field, or of the fundamental group as decomposition groups. So conjugate classes of decomposition groups, and then we'll be able to remove a subset of those, take the fundamental group, see what that fundamental group looks like, and then take this subquotient, which is this cuspidal abelianization. So this thing here, so this is the cyclotome associated to the fundamental group. You actually have to take, so we do H2, I take the fundamental group, or the geometric fundamental group of the curve, compactified, the compactified version of the geometric, so the compactified version of the curve, and then you take its geometric fundamental group, you take that, and then this is the Z hat linear dual. Okay, so we need this cyclotome here. Okay, so this is the tape module of it's isomorphic to the tape module of the roots of unity in the algebraic closure. Okay, and so this thing, so this thing will house this thing, and so this field structure is reconstructed using this so-called Uchida trick. Okay, and it's an incarnation of what's called the fundamental theorem of projective geometry. That's what model theorists like to call it. Essentially, you cook up a way, using divisors, you cook up a way to make addition. So the Kummer map will give you some multiplicative version of this. And then what you'll want to do is you'll want to figure out how to add elements, and you use kind of a Riemann-Roch thing to do that. Okay, so this is the main interpretation, or the main result from Absolute Anabelian Geometry 3 that we need, is to reconstruct this. Okay, so this is the so-called Etale version. It's called Etale because it only depends on this. So maybe it's like holomorphic. Okay, it's holomorphic because I don't know. The holomorphic because you can reconstruct the additive structure from the fundamental group, and it's Etale because it only depends on this and it doesn't depend on a monoid. So then there's also a so this holomorphic Frobenius like interpretation, and so here we start with same thing. So we'll start with a fundamental group, and now we'll start with a monoid here. Pi. Let's take this thing. This is going to be in the class of the set of elements of isomorphic to the fundamental group of this hyperbolic curve of strictly value type here, and a monoid that looks like this monoid of units. So I'm going to use this star here for just the monoid, and then like a cross star will be the units. So Machizuki does a little triangle for that. Okay, and so it's going to be over a p-adic field like before. And so what we do is we will get. So this construction is kind of a modified version of the construction here, and what we'll do is we'll construct. So we'll construct this version of the field pi m bar inside. Here, so the same thing, it's the exact same thing. Pi 1 pi, remove these s's, you take the cuspal anabelianization, and now we're going to switch the cyclotomes here. Okay? Okay. So this is this all sits inside here, and this is going to have the field structure. Okay, so great. So let me. I need to say a little bit more about this, but the point is, one of the points is that here, what we'll do is we'll have. So this is a little k. So this denotes the base field. So this is the field structure k, by the way. So the p-adic field there. So the point is that m star will actually be equal to O k bar pi m bar. Okay, so this will be this monoid in this interpretation. Okay, so these are these two things that we have here, and then we're going to have a comparison between these two constructions, which we'll call the Machizuki-Kummer map. First, I want to say that so how do we get this thing? This field. Okay, well that comes from the second field. So we use that here. So let's call this here m bar. Okay, so this is by definition the groupification of this, and then we're going to do a sequence of maps. Okay, the first map is just a usual Kummer map. Okay, here, and I'm going to denote that limit just by this subscript infinity here. I'm going to do it with an underline, so it's just not all. Okay, so this is just the usual one, I guess. M bar. So this doesn't need an underline here. Okay, and so let me just remind you that so given pi, right, we have this quotient. We can reconstruct the fundamental group here. And so this is defined to be equal to g, let's call it like a fancy g of pi. Okay, and then we'll call this map the quotient. So there's this reconstruction of the geometric fundamental group as the maximal open subgroup, at least in the profinite case, maximal open subgroup of maximal closed normal subgroup, maximal closed normal subgroup of pi. Okay? All right, so we have this map. It goes into here like this, right? So what we'll do is we need to, I mean, there's just so many things that go into this thing. Okay, so this is so this is, in this thing there's two limits that are taken, right? So this is a limit of Kummer sequence maps. Okay, this hat here. This hat denotes the limit over n to giving this thing. And then this infinity is what makes this kind of an algebraic closure. And so that goes over open subgroups, and it's kind of like a transfer map type thing. So, okay. So it's the thing that tells you that when you can include fields. So we can do this one field at a time, and then as you get to bigger fields, you want the smaller fields to be in the bigger fields. Okay. So so this is just the pullback via the quotient. Okay. So now we're doing this weird cuspidal thing. So that's what we're going to do here. So we do the cuspidal anabelianization, and we do over those sets. Okay. Here, pi m bar. This is just the tape module of the given monoid. Okay. And then we're going to do one more map. And this comes from the push forward via synchronization. So this is a cyclotomic synchronization between the one for m and the one for pi. And so we have h1 infinity here of pi, and then we have lambda pi. Okay, and this was the home of our other field. So the field interpreted just in front of the fundamental group. I should say that this. Okay, so we have that. So this is what we have, and then there's so we have this. This map here involves quite a bit. It involves a cyclotomic synchronization using this so-called what much is called positive rational structures, which comes from absolute Anabelian geometry of hyperbolic curves. Okay, so there's lots of things going on. So this is this canonical map between cyclotomes and the induced map here. I guess I could write a little push forward there. Okay, and then what we do is we define, so how do we get the field structure? Right, so, well, okay, so we'll take this thing, k bar pi m bar. So this is defined as a set. It's going to be this thing, m bar here, cross union 0. So this is just, this thing here is just m bar groupification union 0. Okay, plus this field structure pulled back from this map here, from, let's say, k pi here bar, using the map here, and let's call this Kummer map of we'll do the pi m bar to pi. Okay, and so this map here, the Kummer map thing. So this is the composition. So the composition of these is the Machizuki-Kummer map. Okay, so this is what we'll call the Kummer map or Machizuki-Kummer map. Okay, all right. All right, so this is so now we have these kind of two field structures. One which is one's just coming from the fundamental group. The other one that's induced via cyclotomic synchronization. The one that uses this bilinear form. Okay, and what else? So the last thing, okay, so that's what we have. Okay, so we have these two things. So that's the Anabelian procedure for constructing these two things. All right. So now, what does it mean? So what's the official definition of what it means for things to be log linked? So this is from IUT3 definition 1.1. So they'll give log linked Frobenius. So we say that pi m0 is log linked to pi m1. Oh, it's kind of messy. To pi m1, if and only if. So m1 is log post inverse of m0 bar. So in order for this to make sense, this needs to be given a field structure, right? And so so this needs to be contained in this thing here. So k pi m0 bar. So note that this definition. So this is the definition, and we want to note that this definition only makes sense with field structures. By considering field structures, because we have to have the logarithm, right? So we have to have the logarithm, right? So you can't make sense of the integers, right? Without the the integers in a field without a logarithm. Okay, so sorry, without a field structure. So yeah, so that's the point. Okay, so now we want to see how. So going back to like our original thing, we wanted to see how So we wanted to see what happens in a loop of a log Kummer correspondence. Okay, so so let's think about this too. Is that there's another potential issue here. So given, let's say pi m0 bar and pi m1 bar log linked, we can get two field structures on let's say from, or we can interpret two field structures from pi m1. The first from this thing. So pi m1 bar. So this is this is from the Anabelian Geometry 3. So this is the Corollary 1.10 or whatever. And then the other one is from this thing from k pi m0 bar log. Right, so the units of this are m1, right? So by definition, O of k pi m0 bar log star is equal to m1, right? So this is what we had. Okay, so these are the two things that we have. So we want to show that these two things are related, okay? And so let's write down. Let's write down what's going on. So here, so let's write down our two things. So we have m0, right? And we know that this is isomorphic to m1 bar, via log post. And this is actually equal to log post inverse of M0 bar. Okay? So this is the map log post. All right? Then we can now look at the Kummer maps, or sorry, the connecting maps for the Kummer sequence, or the limit of the connecting maps of the Kummer sequence. There's two limits again. So we have this, and then we have the two cyclotomes here. And this is functorial. So this is induced by M1. So this is induced by the push forward of log post. Okay, so then I guess we have to take the cyclotome here. But this is functorial as well, right? Because we have this, so this will be functorial. Okay, now on both of these, we can just pull back by the quotient map Q. They have the same fundamental group, right? And on both of them, we have H1 infinity. Okay, so that weird limit of lambda. Okay, so now we're doing the quotient, so we still have the same cyclotome here. We have H1 infinity underline pi lambda M1 bar. Okay, this also, same thing about the cyclotomes. And finally, for both of these, we have two synchronization maps. Right, so we have this weird thing here. We have this map here, sync. Right, so this is the synchronization, the push forward of the two synchronization maps. Okay, and so this whole thing commutes. Right, this whole diagram commutes. Right, so there's a couple ways of breaking this down. You could say that you could go here and then go all the way over. This all the way over is the Kummer map for 0. So if we were to go all the way around, right, this thing here, that's Kummer 0. All the way around here, that's Kummer 1. And then the fact that this diagram is commutative is just saying that the following. It says that the first Kummer map, right, is equal to the second Kummer map composed with this log post, right, of K1. Okay? And so that's all that it's saying. So this is what this thing is saying. So we do this, right, and then we go over here. So I guess it depends on how you want to label which K goes with which log post. Okay, so I guess the source, I'm labeling it by the source. So we'll have this thing, and then we have this thing, and they commute. Okay. That's great. All right. From our little formula, we can now go back and attack our original problem. So our original problem was, again, so we had this field. This is one interpreted. Then we had this choric field. So this is the one interpreted just in terms of the fundamental group, K1. And then we had this Kummer map here and this Kummer map here. And now we have an explicit description of the Kummer maps, of the composition of those maps, log pre. Okay, and then we had the section which was log post. Okay, and all right, so then we have, this is our setup, and we wanted to know what happened when we went around a loop. When we went around a loop like this. Okay, and so what happens? So let's write this out. So we get, let's write this out. The first Kummer, log K0 pre. The second Kummer, 0 inverse. All right. So, so as it turns out, we can use the formula here, this formula, and we get that this is this Kummer 0 map, right, composed with log post, right, composed with log pre. Right, and then these two are the same thing, so they have the appropriate domain and codomain, cum 0 inverse. And so when you do log post and log pre, So this is Kummer 0 composed with log k 0 composed with Kummer 0 inverse. All right, and now since this is an isomorphism of topological fields, right, the power series are respected, right? So this thing's defined by this is defined by a Q power series, and so we can just bring that in, composed with here log. Now we have log of kc, right? Okay, because this is, we can take the log on the first guy, or we can pull it back and take the log there. It doesn't matter, and these two cancel, of course. And so this is what allows us to conclude that when we go around a loop, we just get a log. So going around, so the point. So again, the upshot, the point. A loop in a log link, in the log Kummer correspondence, is just a log on the core.